we completed the forward pass and the back propagation, and I have explained you how you implement it on the Python manually. So today target is we have seen that the implementation was little bit difficult. We will try to make it easy, or you may say more smart, so that complete code can be written in 6 to 5 lines. And we know what was the difficulty. It is still there. Difficulty is about to calculate the derivative in the back propagation. Okay. So I already sent you these file. You may have done some practice for this one. We were at this problem yesterday, and I have extended this previous problem. This one has one neuron, three input. I have explained each and everything here on the blackboard or the whiteboard. This problem is the extension of this one. So to recall the process, now I consider this problem and write the code again, then make it smart. So I will revise each and everything, forward pass and the back propagation. So right now we have, first we do the mathematical one. Three neuron and we have four inputs. So from each input, there will be a path to each neuron. This way, each one have its own weight. W11, W12, W13, W14, 21. Second neuron weights, and the third neuron weights. 3, 2, 3, 3, and 3, 4. So when there is a forward path and each one have its own bias B1, B2, and B3. So the output here for this neuron from this input, from this input will be W11X1, W12X2, W13X3, and W14X4 plus the bias. If I call it S1, this is the output, and here S2 will be W21X1 plus W22X2, W23X3, and W24X4 plus B. And here output will be W31X1, W32X2, W33X3, and W34X4 plus B. This is 1, this is 2, and this is 3. And then these will pass through the ReLU. So when they pass through the ReLU, so here ReLU will generate ReLU of S1. This will generate ReLU of S2 and ReLU of S3. Let's say this is A1, A2, and A3. After that, now we have a vector here of 3 entries. There is a loss. Loss, okay. Loss will be let's say A, and our target value. To make it easy, I told you I have written this, and this is the mean square. What is this A? A is a vector. A11, A1, A2, and A3. It has three values. It's a vector. And target is not, I have written 0. It is a vector of 0 vector of length 3. And we have to also write 1 over 3 because in a mean square, we have to divide it by the length of the final vector. So there are three entries, so that's why there is 1 over 3. If you use 10, so more, that will be that number. So this is a complete forward pass. And if our loss, if I call it L, is not up to our desired result or close to 0, because our target is to minimize this one. If this is not equal to 0, then we need back propagation before going for the second epoch. Before going to the second epoch, we need back propagation. In the back propagation, we use or we have to update these all weights. So there are 16 weight, sorry, 12 weights and 3 biases. These all should be updated before plugging this input. And we will follow gradient descent. So by gradient descent rule that theta nu, any parameter, is equal to theta old. We have derived this equation yesterday with learning rate and the derivative of the loss function with respect to that old parameter. So this is the formula. So let me do one calculation. So I am doing calculation for W1, how it will be updated with respect to gradient descent. So we need the derivative of our loss function with respect to dw11. So what is it? Loss is a function of these three component A1, A2, A3, and this is a vector of here. So it will be dl over dA. A is a vector here, this A. Then back propagation, and this is passing through ReLU. So dA over d ReLU. A is itself, sorry, ReLU. A is a vector, and if you observe, A11 is ReLU of S1, ReLU of S2, ReLU of S3. A is just a label, so no need of this one. This is a ReLU. So dA over, you may say sum, ds. What is S? S is a vector S1, S2, S3. S1, S2, and S3. And after that, ds over, we can perform dw1. One more. Or if you do in a matrix or a vector form, for all weights, you can write it dw. And this is dw. What is w here? W is 4 by 3 vector W11, W12, W13, W14, W21, W22, W23, and W24, W31, W32, W33, and W34. So finally, our input, if I say X, this is just X1, X2, X3, and X4. This is what we have. So we can do it in a vector or a matrix form. This will work. And for the bias, you have seen yesterday bias derivative at the end is just 1. So you have to just skip this part. So rest is also a derivative of a loss with respect to the bias function. This whole we have to perform the derivative, and then to update the weights, old weights, new weight will be equal to the old weight vector minus learning rate and this derivative dl over dw. Same way for the bias. So this we do before going for our second epoch, before plugging this input. And we again check the loss after the forward pass. If loss is still less than, not close to zero, we repeat the same process. Again, update the weights and so on. So I already sent you this slide. So this is for this neural network. So here, if you label it with the numbers, so weight matrix will have number 1, 2, 3, 4, 5, 6 up to 12, and input vector has number 1, 2, 3, 4, and our bias vector bias has 0 0.1, 0 0.2, and 0 0.3. So now we can implement this on the Python. So this is the Python implementation. So we need a library. Library name is numpy as np. We need to perform linear algebra related calculation. So here, this is for the weights. I myself wrote this one. So I myself label it with the weights. On the right side, we are using NumPy library. Its nickname is NP. That's why I have to written NP. And matrix is written like this one, dot array. First row, then the second row vector, third row vector, then input vector, this one, 1, 2, 3, 4, again NP array, one dimensional vector, and I label it with the inputs. Then bias and NP dot array. So 0 0.1, 0 0.2, and 0 0.3. Then target output, this one, this is our target output. We need that our answer is 0. And then the learning rate. Learning rate is this guy. Where is the learning rate? This one, gradient descent. Then I told you when we do manually without using a built-in libraries formula, we ourselves has to define that function which we have to use again and again. So this is a way of defining. Define, I use ReLU. ReLU, its input vector is input variable is X. Then what it will return the maximum of these two. Whatever you plug here, he compare these two value. Which one is maximum, which is greater than 0, that will appear. Then this is the derivative, and I label it with ReLU underscore D. And what it return? It return, this is like a piecewise function. that conditional statement. If the input number is greater than 0, it will produce 1, otherwise 0. So this is the derivative of a ReLU. We know. Now I am repeating this process 300 times. Okay. See, on the blank page, we cannot perform this one 300 times. Even one time we cannot perform. Okay. So I am performing this 300 times. So forward pass, 300 epoches again and again. So you will see the result that loss is not 0. That's why I need 300 times. So this is a forward pass that you will multiply weights with the input. These weights will be multiplied with input, and it will stored in the z variable. Then that z passing through ReLU, and you will have output. Now this is not a number. Weight is a matrix. Its order is 3 by 4. Okay, and input is a vector whose order is 4 by 1. So the resultant will be 3 by 1. So it's a vector of 3 entries. So that stored in Z, and then that passing through ReLU, and that stored in output uh, variable. After that, I calculate the loss and stored in the loss variable. NP dot mean output minus target output, Eric. Sorry, here 1 over 3 is missing, but I have put here. Okay. Loss. Then for the back propagation, loss derivative. So 2 will come first, loss derivative by power rule. And this is the inside expression, this one. And here I divide with the length 1 over 3. The length of this output is a vector. So 1 by 3. Then I calculate D output, save in the D output, that this is the ReLU derivative. ReLU derivative on this input, and then dA. It is up to you. If you don't want to write, because it is just a vector of 1. Ones like output, its mean, it has 1 entry, 1. If I don't like here in the code like output, so it will stored like this one. Now, by writing that like output, it is stored like this one because output vector was stored like this one in a vertical array. So no need if you don't want. And then dz, this variable is stored inputs only. You can skip this one because inputs already has a vector. This is inputs. Then this is the weight derivative. D loss is multiplying with D output and dA. Then D weights, this is extra if you don't want. Then D weights is NP outer. Because here, why we use NP outer? As I told you, this expression I have written in terms of a vector or a matrix form. This is not a scalar type. W is this vector. Okay. This L is a vector, is the loss. This one, this L inside this A, this information, this is a vector. And same way, A is a vector, S is a vector. S is this vector. And then W is this complete vector, this one. So I am applying the chain rule in vector or a matrix notation. Yesterday I did for a scalar entry. Same way you will perform. But be careful. You should know what is the length of these structures. Okay. The length of this vector, this W is 3 by 4. So at the end, the derivative should have this order. If you are not getting this order, it's mean you are missing some of the weights. You need a derivative of this one, you need a derivative of this one, all on the same position. So final answer for the derivative of the weight should be 3 by 4. This we have to adjust manually. So that's why I am using here np dot outer, and dw is this vector and multiplying with the dz vector. Dz had just the input, and d bias is, there is not a final bar. I told you you can remove this one. This is extra. This is just 1 1 1, because bias derivative is at the end 1 1 1. Because this, where is the bias? This, okay, this is the number form we have written. No. Bias is this vector initially b1, b2, b3. When at the final stage you will find the bias derivative, find the sum derivative with respect to bias. This derivative ds over db is exactly 1 1 1. That's why I use that vector 1 1 1. So weights derivative stored here, bias derivative stored here, and then this is gradient descent. I told you you will use the same space or a storage which you have label, and use this kind of information. It's mean old whatever the data in this variable, it is decrement by on the right hand side. What was the first time here? You are minus learning rate time d weight, then it will again stored in the same variable. It will be automatically updated. The previous data will finish, vanishes, and you will have a new one. Same for the bias. Decrement, learning rate time, debiases, and this is just for the beauty we want to see, we want to print. Here what I have written, if I have written before the print command, yesterday there was only this command. I was printing iteration, and I am not printing from the one, I am printing from the zero, iteration and loss. Here I have put inside the loop, same loop, 300 times it will repeat. So I don't want to see 300 times this print command. What I have put a conditional statement that if this iter percentage 50 equal 0, this is the syntax. It's mean when you perform your first 50 iteration, then print this. Don't print first iteration, second iteration, third iteration. When this loop run for 50 time, first 50 time, answer will appear. Then next 50 time, so then next 50 times. So in 300, how many times? 6 times we will see this answer. And this one outside the loop. So what it print? It will print. This is I myself have written. That's why in the red line. Final weights. You may write your name here. So weight variable will appear. Final time outside the, after working 300 times. Whatever the answer for the weight matrix will appear, and whatever the answer for the bias matrix, that will appear. If you run it on the editor, you see. So after every 50 iteration, the answer will appear. First time loss was 2070, and after 250 iteration, 0.0, close to 0. Till I did, we can't see the 300 time, the last iteration. So for that one, if you put iter plus 1, then you will have a 300 iteration here. Okay. I told you it will loop work until the end of this number. He will not show you this 300. Okay. He will run start from 0, and it will run 300 times. If you count from 0, it will be 299. That's why we are not watching this one. So these are the final weight matrix. Initial weights are 1 2 3 4 5 6 7 8 9 10. These are written after 300 time. When loss become this one, or I think more close to 0, weights have this form and bias has this form. So this is what we have seen yesterday also, that whenever we have a neural network, how we can write or implement on the Python. Okay, let me show you this thing on the Python also. So I told you you can use the editor Google Colab right in the Google because I already have some data here. First time you see here is a new notebook written. You can click on it, but I am not clicking here. I already have stored this code. I just want to run and show you how it is working. So this is the code. The green one is just a number. This is I myself have written. And the rest is the code. The same code I have shown you. Is that one? No, no, not this one. File. Yes, this is the same code which we have seen on the slide. This one. So let me run it for to execute it. You may use this one or you may use a runtime. If I execute, it will take to connect with the internet and then it will take its time to run. So cursor is moving, it's mean it is working. If you want to stop in between, you can click on this the circle. But right now I am not. So it has done. So there is a tick mark, correct mark. It means there is no error. So this is a result at the bottom. Same result, 2017. And after 250 iteration, we have this and the bias. So this is the implementation and this is the mathematical work. Now we will, yes, sorry. हम्म, हम्म, हो रहे हैं ये हर आइट्रेशन में अपडेट हो रहे हैं लेकिन मैंने प्रिंट ही फाइनल कराए हैं 300 टाइम फॉर एग्जांपल लुक एट हियर यस लेट मी शो यू if I want to run it only one time, so at this place I will just write one. Okay, so it is done. Now these are the weight after first run. So now I have run the same code one time. Now the weights are, you may say loss is first time 2070, okay, and the weights are 0.97 and biases are this one. So after writing the code, it is up to you. You may run it 3,000 times, 1 million times. Same code will work. Okay. So this is the beauty of writing a code because this is the calculator for our physics informed neural network course or artificial neural network course. If I do this thing on the page with the pencil, I will not be able to solve even for the one time. Okay, that's why we need this one, and that's why I am explaining you. Is it clear? The code, right? No, code is difficult. I know difficult. Difficult part to handle these back propagation, and this is very easy neural network still. Okay, so we have to generalize this neural network. For example, if we have second and the third layer, how we will handle the back propagation? That is more difficult. So, so I will now go for little smart code as compared to this one using the built-in library. Okay. Then there will be a next stage smart code. So first I will explain you the middle stage smart code. So look at here. Target output is in the vector form, like this one, 0, 0, 0. कोड में एक तो ये मसला करता है हमारे लेक्चर 3 दिन से मसला है कोड में target output, because I told you this machine is more smarter than us. I have just tell him 0, so he automatically adjusts. Nothing. For example, in the code we need a vector of length 10, so he automatically generate that. But if you have a target output other than the 0, it may work for only for the 0 or for the 1, but not for other values. So this is our difficult code, but this is the exact implementation of this mathematical work. Okay. Any question? Then we move to smart code. No? Oh, yeah, right. So, कहाँ पे? Uh, ये यहाँ पे loss. Okay, because he don't know what is a mean square formula. What I have given him, he is considering mean square formula. If I use built-in mean square formula, then he know this is the exact formula. Okay, this is our code. So this will become this one, smart code. And most of the difficult part will remove. How? So here, what is the difference? I am using this library, torch. Here I am using a simple library that's only perform linear algebra calculation. But this is more smarter library. It has so many information which we can use and which will be helpful. You have to first use import torch, and from this library a second part. It also has some sub libraries, torch.nn. NN mean neural network, and its nickname is NN we will use. So whatever the thing we write, look at here. Here input variable is NP due to this library. Okay, now we are inside the torch, so we have to write torch. And torch is more general. So it started from a tensor. You know what is a tensor? Scalar, then vector, then matrix, then multi-dimensional vector. That is tensor here. Okay. So it is a general library. So every time you have to write a tensor, even you are writing a vector, simple vector here. So these are the same thing. Just you have to replace NP with the torch and its syntax. What is important? Look at here. This is the ReLU derivative, which we have manually defined in our simple code. Can you find where it is written in this code? Just one time in a simple command, nn dot ReLU. This blue part automatically written by this torch library. You may memorize this one. Every time you have to write this one, nn dot ReLU, only and open bracket. If you use an other activation function, for example, 10, so you will write nn dot, let me write it, nn dot 10 h and open. So no need to define, simple. Just write one word, so everything automatically calculated instead of defining from the first principle. Clear? No, it is easy. I am coming. Now the dangerous part was the derivative in the back propagation. Look at how easy. This part control the derivative. Just two lines you have to memorize. Nothing else. Model dot zero grad, because it has to initialize from the zero. Even you ignore this one, it will automatically adjust. Just one line, loss dot backward. Loss dot backward in every code. Whatever a lengthy code, just write loss dot backward and open bracket. That command will control this one. Whole derivative structure. Even this is A huge neural network, just one time you have to write loss dot backward and open bracket. Okay, now it is easy. Yes, rest, if you observe here, this is just for to see the print information, same like here. Okay, but here you have to write like in a model and 0 0. Okay, so rest code is already easy, just the input data. And the most beautiful thing which you are not observing right now is this one. This is the most powerful statement. For a forward pass, when we write a forward pass manually, it controlled by this command, model. Model inside the inputs variable only. Just you have to give input vector and write model. Inside it's whatever your input data, where you have stored the input data, you will plug here and write the model. So that command will perform complete forward pass. Okay, but with that one, this part you have to write at the beginning. This control this whole neural network. Our neural network has four input and three neuron. So you have to write nn dot sequential. This is the syntax for this one. Then there is a bracket, okay, and nn dot linear, because first we have linear calculation, and first one is for the input 4 and second one for the neuron, number of neuron. Just write this command. So this whole information, the forward pass is controlled by these two things. So this is just a middle level smart code. I will make it more smart. Okay. Is it easy or not? Instead of writing this whole information, you just write these three information and rest is your input data, and front the top one is the import of the library. So try to remember, memorize these three statement and the sequential one that control each and everything in a neural network program. Okay. So when you go back again, I advise you try to write by your own hand this one. So every complete forward pass is controlled by the model and NN sequential, and complete back propagation is controlled by one command, that is loss dot backward. Automatically all derivatives have calculated, initialize whatever stored. We don't need to store them automatically inside. But you should know, for example, if I start the course from this code, can you understand? You can feel. Can you understand what was happening background? So that's why I started from the zero. First, I myself write the code manually. Then I make it in a, you may say, automatic form. That what command control this information. So, and this is, yesterday I told you, the complete cycle of every artificial neural network, whatever. So this one, a middle level smart code. Clear? Now, if I tell you, instead of this neural network, we have a neural network. It in first row has 100 neuron and input has 50 values. So what you do in this code? Just you have to change that number. 4 is replaced by 50, 3 is replaced by 100 and nothing else. Same will work. Okay. If I tell you 1 million, 2 million, yes. Yes, that's right. So you have to change your input data. Okay, 50 iteration and sorry, 50 length vector and the weight matrix, this one. What will be the size of a weight matrix? It will be 50 by 100, 50 by 100 matrix. Okay. So this is why I told you this is the middle level smart code. There is another smart code after that. So first I am playing this one. Everything is okay with this code? No, the next level smart code. A brother told me yesterday a question, why we initialize weights by ourselves. So I explain, for a neural network, when you implement on the Python, whatever the neural network, first time it's needed a weight. It is up to you whether you give him a weights, whether he himself randomly collect those weight. Okay. So yes, he is right. In our big problem, we don't initialize weight because this is like an initial guess. When we solve a numerical method, we need to start somewhere. So this is like an initial guess. So no need to give weights and biases. That is controlled by one command. Look at here. Is it clear? Now from this code, I will not give a weights because in your pin coding, no need to give initial weights. The code automatically or randomly selected that one. So this one was our middle level smart code. So this is the final stage smart code. So these initial weights and biases is controlled by just this command. Yes, even you don't write, he will catch. But this command has some beauty. Torch dot manual seed 1, 2, 3, 4. What is the beauty? For example, you have made the code, you run the code, the Python randomly selected weight versus whatever the parameter with this with if you do without this command, okay. But with this command, what happened? You run the code, you get a result. You close the Python, you or friend or you open the Python again and run the same code. What this code do? He randomly selected the weights and biases, but for every time he changed the initial guess, initial weights. But if you write, because when we do in the physics informed neural network, we need the same kind of initial guess every time to test that problem. So that's why you have to write torch.manual underscore seed. You can memorize it and 1, 2, 3. This one. So this one command is doing for this one. And I told you this part is just for a beauty. We have to see the data. So this is the simple. Every it because we have four inputs, so 1, 2, 3, 4. And if you have five, you can write five and so on like that. But sometime you just put the open bracket, that will also work. Okay. So look at here. If I remove the last part, that is for just to show what information is on the code. Okay. So the rest code is very easy. Just you have to import these library. You have to put your input. You have to put your target value, value or vector, and the learning rate. Okay. Then model, you can change this word, but I use model every time. NN dot sequential and NN linear because four input, three neuron, and passing through ReLU, and this bracket close. This structure is for the neural network. Now, whenever you see this one, it will appear in front of your eye that your artificial neural network has four input and three neuron. Then this is for epochs. For iter in range 300, output will be stored due to this model. Just you write model and inside it write the inputs, whatever your inputs. Then loss, this is a mean, and I write torch dot mean. Here I will not divide it by whatever the entry is because it's a built-in command mean. Torch dot mean output minus the target, and you have to put the scare too. And after that, you have to write model dot zero underscore grad, open bracket, loss backward. So whole back propagation. Every time you have to write, you have to just memorize this one. This part will not change. This part will not change. Only this part also not change if you don't change the loss. Input will not change. Don't change this one. Don't change this one. Just change your input data and everything automatically done. So this is, there may be more smarter than this one. You yourself do that one. So this is somewhat the smartest level code for this artificial neural network. Is it clear now? Okay, one small. Now my neural network. So first layer, layer one has four neuron. Previously we had three. Okay, three neuron. Second layer has four neuron, or let's say five neuron. This is also passing through ReLU. This is also passing through ReLU. Where do I change? Can you guess? First layer is written already there. Yes. So what you do, previously we have written model equal nn dot sequential, and there is a bracket, and we have written nn dot linear, and 4 comma 3 comma, and it is passing through ReLU, nn dot ReLU, this one. So now we are adding another layer which have five neuron, 1 2 3 4 6, okay, six neuron. And so what are the inputs for this one? Our inputs is three, the previous layer neuron. So what you do, you will write another layer, nn dot linear. Here you write three input and six, and nn dot ReLU. But for the previous ReLU, you have to put comma. For the last one, we don't put comma. Okay. So this way you can extend. If I made another layer, layer 3, and I say it has 100 neuron. What I need to do? Just I have to extend this one, nn dot linear. So its input neuron are 6, and then 100 and comma here. And for the last one, and then for example, I passing through it 10 hyperbolic. So what I do? Nn dot 10 hyperbolic and open bracket. Simple. So just you have to know how to control the neural network structure in the Python. So memorize this information. This is important. Each and everything is just for the data, whatever the data you plug. So if someone asks you, do you know how to write the code for artificial neural network? He's asking this command from you with the torch library. There are other libraries also. Just write, you may say, I am using torch library, and for the nickname for the neural network is NN. So this command will control whatever the size, million neuron, 2 million neuron, how much is the bigger. So you have to write nn dot sequential, and inside you can put the structure. So now to make a code for artificial neuron is, I think, easy. And for back propagation, just one word, loss dot backward open bracket. This one word can control each and everything. I think no, you may feel happy if you want. This is the maximum I can tell you. Yes. Yeah, forward path. No, This control the structure of the neural network, whatever type of a neural network, because you write manually here. Okay. Secondly, yes, with the sequential, it automatically calculates the forward pass between. Any other question? Activation function कभी linear नहीं है. It is depend upon us. What activation function we are using in between the layers. Okay. For the first layer, I am using ReLU, so I put ReLU here. Okay. For the second one, I am using ReLU, I put ReLU. For the third one, this one, I am using tan, so I will put a tan here. Just the activation function I already explained you. It is converting linear information to a non-linear information. Okay. Any other question? Same way. Same way. Input, man. Yes. For an input, for example, you have a. I am giving a simple input, a vector of with four entries. Okay. And for example, you have a huge data. Okay. So there you yourself have to become smart, but how you handle that data. This is another thing to handle that one. But I know there is only a tensor form, scalar, vector, matrix, and multidimensional tensor. Okay. But in other artificial neural network like CNN, convolution neural network, we mostly do image processing task. Our input are not the vectors, those are the data of the figures. And also, you don't put data manually like this one. When you have a big data already stored in the on the internet in some libraries like GitHub. Okay, there is just one command. You recall that data. You yourself don't tab with that data every time. First, then second setting. To do such task, data is already available on the internet. You just need a one command. I am not giving. I myself don't know the command. Whenever I need some data from the internet, ChatGPT give me that command or import that data. It is same like the import. You write import and write the name of that repository. That will call. Any other question? So this is the enough from artificial neural network. Yes, there are other smart way. There are so many other things. Tomorrow I will switch to physics informed neural network. If you have any question related to artificial neural network, I may ask you. We have a time. रियल लाइफ सिनारियो आई है इसमें क्या किया है मैंने एक सिंपल एग्जांपल से समझाया है कि फोर एंट्रीज हैं और कल भी मैंने कहा था हम किससे लेबल कर रहे हैं एल